start recording. So the numerical relationship between chemical quantities in a balanced chemical equation is called reaction stoichiometry. That's the big fancy word. If you want to Google this, like, if you want to read up, get somebody else to explain it on YouTube, or look up more information about it, stoichiometry is your keyword. I know it's a hard one to remember because it's such a weird word. But this process allows us to predict the amounts of products that form in a chemical reaction based on the amount of reactants. These calculations are central to chemistry, right? Trying to predict what chemicals are doing. So like stoichiometry, a recipe gives us numerical relationships between the ingredients, the reactants, and the number of pancakes in this case, or the products. So it takes a certain amount of flour, eggs, and baking powder. Of course, this is a simplified recipe, right? You need like oil and milk and other things. But in the simplified recipe, you need these quantities, these exact quantities of these things, to make 5 pancakes. If you don't have enough of any of those things, you can't make 5 pancakes. You can only make fewer than 5. So if we have 2 eggs and more than enough of everything else, and usually that's the case, right? Baking powder comes in like a can like this, and you use half a teaspoon of it to make 5 pancakes if you're making pancakes. And flour comes in large quantities too, and they keep for forever, but the eggs don't keep as long. So let's say we only have 2 eggs, but we've got plenty of flour and baking powder. Then we can make 5 pancakes, right? We're not going to run out of anything else, limited by the number of eggs. So we can write this relationship as a ratio, and we're pulling these numbers straight out of this recipe. Right? So for 2 eggs, we can make 5 pancakes, which this should look a little bit familiar because it's a conversion factor. Right? Let's just convert between number of eggs and the amount of pancakes that we can make. So we don't need to just have 2 eggs, right? We could double this recipe, or in this case, quadruple this recipe. If we had 8 eggs, right, which is the number of eggs we would need for a quadrupled recipe, 4 times the amount. And if we have enough of everything else, then we can take those 8 eggs and the other ingredients and turn it into 20 pancakes. Right? So it's not just for 2 eggs. We can multiply this and make even more. So while recipes are instructions for how ingredients combine to form other foods, chemical equations are instructions for how atoms or molecules combine to form new molecules. So this is really, it's like an outline. It's like a template. It tells you if you put these things in, you're going to get other things out, and in specific quantities. So if we take this over to a chemical reaction, in a balanced chemical equation, we have a recipe for how reactants combine to form products. In this case, we have a synthesis reaction, right? We're taking 2 simple things and we're making something more complicated. We're taking hydrogen and nitrogen and combining them to make ammonia. And just like with our eggs to pancake ratio, we can derive those ratios, similarly derive ratios from this chemical equation. So if we had, and these are mole ratios, if we have 3 moles of H2, or hydrogen, we can make 2 moles of ammonia. If we have 1 mole of nitrogen, we can also make 2 moles of ammonia. And we can even derive ratios between our reactants. So we could say, well, if we have 3 moles of H2, how many moles of nitrogen are we going to need to use up that hydrogen completely? So that'll be 1 mole of nitrogen. So while in our recipe for pancakes, we have specific units, right? We have 2 cups of flour, 2 eggs, which is a unit sort of, and a half a teaspoon of baking powder. We have to use the correct units for the recipe. So if you used, gallons of flour, 2 gallons of flour, 2 eggs, and a half teaspoon of baking powder, you would get really terrible pancakes. In fact, you'd really have just flour. So in the recipe that is a chemical equation, the units are always moles. So you have to be converting from moles of something to moles of something else. So you put this into practice. If we have 3 moles of nitrogen, more than enough hydrogen, right? This is like our 2 eggs and more than enough of everything else. How much ammonia can we make? I think the best place to start on these is to just say, yes, we'll be 6. But we can start with figuring out which things we're actually working with here. So we're going to start with our 3 moles of nitrogen. And we can pull out of the chemical equation a ratio between nitrogen and ammonia. So, oops, it's not 3. It's for every 1 mole of nitrogen, we'll make 2 moles of ammonia. And as I mentioned before, this is just a conversion factor. So if we have units, moles of nitrogen, we'll take moles of nitrogen from our ratio. We'll put that on the bottom. And then we'll take the other part of that ratio, which is the 2 moles of ammonia. So this is really just another way to write out unit conversions, where each vertical line you're multiplying across that and then dividing by everything on the bottom. So we just take 3, multiply it by 2. As somebody whispered earlier, we have 6 moles of ammonia that we can make with our 3 moles of nitrogen, assuming we have enough hydrogen. So as I mentioned on the previous slide, if we wanted to know how much nitrogen we would need to completely react with 7.13 moles of hydrogen, we can do that as well. The ratio, again, just comes from our balanced chemical equation. So we'll start with 7.13 moles of hydrogen. Whoops, that didn't work. And then the ratio between hydrogen and nitrogen, 3 moles hydrogen. For every 3 moles of hydrogen, we'll need 1 mole of nitrogen to react with it. Oops. So again, because we have moles of hydrogen, we're going to put moles of hydrogen in the denominator, and we'll put moles of nitrogen in the numerator. It's going to reach. Okay. Yep, moles of nitrogen in the numerator. So we'll get 7.13 divided by 3 moles of hydrogen. And we'll get 2.38 moles of nitrogen. is what we would need to completely react with the amount of hydrogen that we have. Any questions? All right. So we can form water when hydrogen gas reacts explosively with oxygen gas, according to this balanced equation. This is what happened to the Hindenburg. How many moles of water result from the complete reaction of 24.6 moles of oxygen? Assume that there's more than enough hydrogen. For the most part in these problems, the way it's worded doesn't matter so much, for the most part, right? Because, even though this is asking how many moles result from the complete reaction, we can just say we have 24.6 moles of oxygen. That's reacting, forming water. How much water is going to be made? And so this is just like the recipe. We just use our 24.6 moles of oxygen, the ratio from our balanced chemical equation. Start with our 24.6 moles of oxygen. And what is our ratio between oxygen and water? How many moles of oxygen to water for every moles of, oxygen to water? We'll just use the coefficients from our balanced chemical equation. So for every 1 mole of oxygen, we can make 2 moles of water. So if you want to write that out, that's 1 mole oxygen to 2 moles H2O. So 1 mole oxygen, 2 moles H2O. So we just multiply 24.6 by 2. And when we react all of this oxygen, we make 49.2 moles of water. So the ratios for these problems, the conversion factor that you use, always comes from the balanced chemical equation. But, and we talked about this before, moles aren't the most useful unit for weighing out things or figuring out, how much water is 49.2 moles of water. We can't go and weigh that out on a scale. There aren't any scales that read out in moles. You can't pour it into a beaker that reads out in moles. So instead we use, most of the time, mass as sort of a first layer, right? So you can weigh out an amount of water and figure out that mass and convert that mass into moles. So it was just the last chapter? No, it was chapter 6 where we talked about molar masses and molecular masses and converting from grams to moles, moles to grams. This is where that comes into play in a big way. Right. And this is where I was talking about too. In a lot of problems, you'll be given grams. And if you're asked to find grams of a different compound in a balanced equation, we can't use grams and then go straight to the molar ratio and then to the mass of our other compound, because the units that we use for the chemical equation are always in moles. So you'll convert from mass of A to moles of A, then we can use the the ratio from the chemical equation to convert from moles of A to moles of B, and finally convert it into a mass of B. So what mass of carbon dioxide is emitted by an automobile when 5.0 times 10 to the 2 grams of pure octane is burned? So we're going to follow that outline from before. And again, always identify we're doing octane, and in a exam type question, I would tell you that this is octane. You wouldn't need to just know that that's octane. For other stuff, ionic compounds, that kind of thing, I will expect you to know that. So we've got a mass of octane, and we want to get a mass of carbon dioxide. So starting out with our 5.0 times 10 to the 2 grams, I'm going to abbreviate this as oct. Our first step here is going to be to convert from grams of octane to moles of octane. So we can find the molar mass or the molecular mass of octane using quantities from the periodic table and the individual masses of the atoms and the number of those atoms in a molecule. So in octane, we have 8 carbons, we have 18 hydrogens. The mass of carbon is 12.01. For hydrogen, it's 1.01. You can, of course, find that on the periodic table. So carbon up here, 12.011. And then hydrogen over here is 1.008. So I'm rounding a little bit because I'm going to run out of space on almost all these problems anyway. So once we have those individual masses, multiply the number of carbon atoms by the mass of carbon. So 12.01 times 8 be 96.08. 1.01 times 18 will be 18.18. And then we add those together. So that our mass of octane is 114.26 grams per mole octane. So remember, grams per mole, this is 114.26 grams per 1 mole. That's our conversion factor between grams and moles of octane. So we'll divide by this 114.26 grams of octane and convert it into moles of octane. So now we've converted from grams, put grams of octane to moles of octane. So what should our next step be? If our ultimate goal is to get grams of carbon dioxide. Moles of carbon dioxide, yes. So we get the moles of carbon dioxide from our ratio in the balanced chemical equation. So what is our ratio between octane, which again is this one on the left, and carbon dioxide? It's the coefficients. Yep. For every, sorry if that's messy there, 2, yeah. So for every 2 octane. So yeah, we want to get, for every 2 moles of octane, we can get 16 moles of CO2. So what's our last step then? . convert to grams. So now we can get grams of CO2. And we'll calculate the molecular mass for CO2, again using the periodic table. So we have carbon, which has a mass of 12.01. Actually, I've been doing this in this order. Sorry, there's one carbon, and there's two oxygens. Carbon is 12.01, oxygen is 16.00. So this is going to be 12.01 and 32.00, so it'll be 44.01. That's grams per mole CO2. So to convert from moles of CO2 to grams of CO2, write this as 44.01 grams of CO2 per 1 mole CO2. And then just like every other conversion problem, multiply everything across the top, divide by everything on the bottom. So 5.0 times 10 to the 2 times 16 times 44.01, and then divide by 114.26, divide by 2. So we'll get 1.5 times 10 to the 3 grams CO2. Any questions now? All right. Keep going. Lots of examples today. So what mass of octane would be needed to generate 42.3 grams of water? So now we're working with mass of octane, grams of water. So we'll start with the number that we're given, which is 42.3 grams of water. So it starts us off with grams. And then we'll convert that from grams of water to moles of water. With the molar mass. So for water, we have hydrogen and we have oxygen. 2 hydrogens, 1 oxygen. Hydrogen has a mass of 1.01, oxygen's a mass of 16. So it's going to be 18.02 grams per mole. Water. So do we put this 18.02, does that go on the bottom or the top to convert from grams to moles? Bottom, yeah. Because we have grams here, so we need to put grams on the bottom to cancel out those units. Because that 18.02 grams is 1 mole. All right, so we got moles of H2O. Now we want to get moles of octane. So it's a ratio between water and octane. How many moles, whoops, I don't want to write this. How many moles of water to how many moles of octane? Sorry, this one's octane. Yep. 2 moles of octane for every 18 moles of water. Or 18 to 2, 2 to 18. It's the same thing. So then just like we had grams, here we want to cancel out grams. We have moles now, so we want to cancel out moles of water. So this will be 18 moles of H2O, 2 moles of octane. And then we'll go from moles of octane to grams of octane. Again, using our molar mass, which we calculated on the previous slide, 114.26. So if before we divided by grams of H2O to convert from grams to moles, we now want to multiply by grams to get grams. So our question originally asked us for a mass of octane from a mass of water. So we started with mass of water in grams, converted from grams to moles, or moles of water, I should say, then to moles of octane. And then this will get us grams of octane, which is the thing that we're looking for. So we just multiply across the top. 2 times 114.26 divided by 18.02 divided by 18. And so we'll need 29.8 grams of octane to produce 42.3 grams of water. Yeah. Yeah, so 29.8 because it's 3 sig figs, because we started with 3. Any other questions? Yeah. That's the molar mass of octane. So because this is actually the same reaction as this slide, we calculated it over here, so I just took the number. So yeah, it's up here. So yeah, it's always the molar mass or molecular mass is always the number of atoms of a type multiplied by the mass of that atom. So 8 by 12.01, and then hydrogen is, there's 18 of those times 1.01. Anything else? No questions too simple. Okay. Magnesium hydroxide, the active ingredient in milk of magnesia, neutralizes stomach acid, primarily hydrochloric acid, according to this reaction. So how much HCl in grams can be neutralized by 5.50 grams of magnesium hydroxide? How should we start this problem? Now that you've seen me do a few of them, what number should I write down first? What's given? Yeah, so 5.5 grams of magnesium hydroxide. I should move this over. Okay, good start. So if we have grams of magnesium hydroxide, then our next step, grams to moles. And how do we get moles of magnesium hydroxide? Molar mass, yes. So we'll have magnesium, oxygen, hydrogen. And then remember that, oh, thank you. Remember that when you have parentheses like this for a compound and a 2 outside, or any subscript, right? So the small numbers to the bottom right are subscripts. That multiplies by all of the atoms inside the subscripts. So we have 2 oxygens, and we have 2 hydrogens, and 1 magnesium. I know these two off the top of my head. It's 16.00, 1.01. For magnesium, though, we'll pull up the periodic table, which is probably very hard to read in the back. Yeah, 24.305. So this is going to be 24.3. I guess I only have to write it out here. So 305. So I don't need a calculator. 24.305. And then this is 32.00, 2.02. And then we add those numbers up. And we'll get 58.325 grams per mole magnesium hydroxide. So we'll use this, and again, if we have grams, we want to divide by the molar mass. So we'll divide by 58.325. That's grams of magnesium hydroxide. That gives us 1 mole magnesium hydroxide. What do we want? Oh, HCl. So remember, we're going to grams of HCl from our magnesium hydroxide. So it's a ratio between hydrochloric acid and magnesium hydroxide. Somebody new? Somebody from the silent back? The ratio between magnesium hydroxide, hydrochloric acid, just their coefficients. It's the number in front of, magnesium hydroxide, HCl. Yeah, 1 to 2. Yeah, 1 to 2. So if there's no coefficient in front, it's an implied 1. And hydrochloric acid has a 2. So we'll take our ratio there, 1 mole magnesium hydroxide to 2 moles of HCl. And then finally, we need to find the molar mass of hydrochloric acid. It's the one hydrogen, one chlorine. 0.01, 35.45. Oops. And again, I just have some of these memorized from doing it so many times. You can always go to the periodic table. All right, so for chlorine is over here, it's 35.45. So the atomic mass. So it's going to be 36.46. That's grams per mole HCl. So if we have moles, then you multiply by molar mass. 36.46 grams of HCl, 1 mole of HCl. That will get us where we're trying to go, grams of HCl. And we just multiply across the top. So 5.50 times 2 times 36.46 divided by 58.325. And we'll get 6.88 grams of HCl. If you have any questions, please ask them. This is like super critical for like the rest of the class. And it's going to be a big focus of the next exam. Never too late to ask a question. Okay. There are no questions. So one component of acid rain is sulfuric acid, which forms when sulfur dioxide, a pollutant, reacts with oxygen and rainwater according to the following reaction. Assuming that there's more than enough oxygen, oxygen and water.
May I have your attention, please? This is password IED.
How much sulfuric acid in kilograms forms from 2.6 times 10 to the 3 kilograms of sulfur dioxide. So we got that one there, and then we want this. And it's always a little bit tricky when the units get switched up, because here we're working with kilograms now, and not with grams. So we're going to have to add an extra step in our problem to convert from kilograms to grams, because the units of molar mass are grams per mole, not kilograms per mole. So we'll start again with the number that we're given, 2.6 times 10 to the 3 kilograms of SO2. As I just mentioned, we'll have to convert from kilograms to grams, which is a metric conversion, multiple of 1,000. So there are 1,000 grams for every 1 kilogram. Sorry, I did that upside down. 1,000 grams for every 1 kilogram. So we want to go 2 grams from kilograms. So we have started with kilograms of SO2, going to grams of SO2. Now we want to go to moles of SO2. So we're going to need the molar mass. I do not remember what sulfur is. It's 32 something. 32.066. So 32.066. All right, because there's only one of those, so 1 times that. And then there's 2 oxygens times 16.00. So it was 32.00, 32.066 will give us 64.066 grams per mole SO2.
May I have your attention, please? This is Atlas IED.
So we'll put that 64.066 grams of SO2, 1 mole SO2. All right, so if we're converting from SO2 to H2SO4, what's the ratio between those two? The molar ratio. Somebody knew. What's the coefficient in front of 2? Or what's the coefficient in front of SO2? 2? I saw some hands in the back. All right, 2. So there's 2 moles of SO2 for every 2 moles of H2SO4. So 2 moles of SO2, 2 moles of H2SO4. And that'll get us to moles of sulfuric acid. And then we need to go from moles of H2SO4 to grams of H2SO4. So it's another molar mass, hydrogen, sulfur, oxygen, 2 hydrogens, 1 sulfur, and 4 oxygens. This will be times 1.01, 32.066, 16.00. So this is 64.00. So just add those up now. .86 grams per mole. Whew. Are we done there? One more step. Almost done. But we have to go to kilograms. So that'll be just the reverse of what we did up front. This is where I'll tell you that there's a shortcut in this problem. I wanted to do it all out first because unless you know how the shortcut works, you shouldn't take the shortcut. In this case, we're going from kilograms to kilograms. And as long as you have a metric unit of mass, and you're starting with, or you're ending with the same unit that you started with, you actually don't have to convert it, because if we look at the math that we're about to do, we're going to multiply by 1,000, and then we're going to divide by 1,000. So if you multiply something by 1,000 and divide by 1,000, you undo that process. Similarly, because we have a molar ratio of 2 to 2, that also reduces to 1. So we're going to multiply by 2 and then divide by 2. So if you know what you're doing, there are some shortcuts that you can take. So I'm going to take those shortcuts. But even if you don't take those shortcuts, we should end up at the same answer. So I'm doing 2.6 times 10 to the 3 times 98.086, and then dividing by 64.066. 2 sig figs here, so we're going to get not enough space to write the answers, what we're going to get. So it's an arrow. So it's going to be 4.0 times 10 to the 3 kilograms of H2SO4. And that's because it's 3,980. So with 2 sig figs, we round that up, get 4.0. Any questions? These really are just conversion problems. The trickiest part, maybe, is remembering where the conversion factors come from. But aside from kilograms to grams, they're all calculated. And they come from either the balanced chemical equation, or they come from the periodic table in terms of molar masses. So you're not going to have just a table of conversion factors for any of these. The closest you get to that is a periodic table. So it rolls into sort of the next level of this. Right, we built this base, we can convert grams to moles to grams, which I do like to call the Gramwich, converting those. But what happens if you don't have enough of something? So in this case, we have 3 cups of flour, 10 eggs, and 4 teaspoons of baking powder. How many pancakes can we make? I think in, IRL, out there in the real world, if you're doing this, you'd probably just start making pancakes and figure out how many you get to. But the way we can do this mathematically is just start with each quantity and work it out as if we have enough of everything else. So just using our 3 cups of flour, let's figure out how many pancakes we can make with that. So with just 3 cups of flour, our ratio for flour to pancakes is 1 cup of flour for 5 pancakes. So that'll give us 15 pancakes. Okay, cool. Based on that amount of flour, we can make 15 pancakes. But now we'll move on and we'll say, okay, let's say we have 10 eggs. Assume we have enough of everything else. We start with our 10 eggs. Our ratio for eggs to pancakes is 2 eggs, again, to make 5 pancakes. So we'll say 2 eggs make us 5 pancakes. So that'll give us 10 times 5 divided by 2. So 10 times 5 is 50, divided by 2 is 25. So 25 pancakes. It's like, okay, well, looks like, that was weird. Looks like actually if we started making some pancakes with the 3 cups of flour, the 10 eggs, the 4 teaspoons of baking powder, we would run out of flour before we ran out of eggs. So the most we can make, as far as we know right now, is 15 pancakes. But we might be limited by baking powder. So let's see if we have 4 teaspoons of baking powder, which I'm going to abbreviate, BP. Our ratio of baking powder to pancakes is half a teaspoon of baking powder. So 1/2 teaspoons of baking powder to 5 pancakes. So we do 4 times 5 will give us 20, and then divided by 1/2, which means we're actually multiplying by 2, it'd be 40 pancakes. So our limiting ingredient here is flour, right? We can, with the amount of flour that we have, we can make just 15 pancakes. We'd have extra of everything else. So if this were a chemical reaction, then our limiting reagent or limiting reactant would be the flour. And then 15 pancakes would be our theoretical yield. So based on, whoops, didn't mean to do that. Based on this amount of ingredients, we can only make 15 pancakes. So in theory, if we did this perfectly, we'd get 15 pancakes out of that recipe with those ingredients. But as we all know, nothing ever goes perfectly. So if we are cooking our pancakes and we accidentally burn 3 of them and then drop one on the floor and our dog eats it, even though we had enough flour for 15 pancakes, we didn't successfully make 15 pancakes, but we only made 11. So in terms of a chemical reaction, 11 pancakes would be our actual yield of pancakes. So the amount that we actually make in the reaction or while we're cooking. So we can take that actual yield and our theoretical yield and calculate a percent yield. So what percent of the pancakes did we make successfully? If we take our 11 pancakes, which is our actual yield, and then divide it by our theoretical yield, multiply by 100, we get that we can only make, or that we only got 73% of the pancakes that we set out to make. Can I delete this? Nope. So the process then, if we take this from the cooking analogy into the chemistry, ends up being the same thing, which we'll get to examples in a second. Pretty much all the time you don't get your theoretical yield. There's always less than 100%. Sometimes it's just because that's the way the reaction is. I think in undergrad we had to do this. It was a really, really, really long process. Our professor went to the butcher and got a fresh cow heart from that morning, brought it to lab. This is for biochem. And we had to isolate over the course of the semester an enzyme from it. So you had to get the really fresh stuff because it degrades quickly. And I think the highest yield anybody got was 10%. Maybe 10%, probably less. I think there was somebody who had 1%. So through any step, at any process where you transfer something to something else, you're going to lose a little bit, right? It's like when you make pancakes even, you're leaving some batter in the bowl. You're leaving some batter on the spatula. It's in the mixer. It's between the various things. So there's almost always less than 100% recovery. It's just the reality. So to summarize though, the limiting reactant is a reactant that is completely consumed. So you use it all up. It's also the reactant that makes the least amount of product. The actual or the theoretical yield is the amount of product that can be made with the limiting reactant. Your actual yield then is the amount of product that you actually make. And it can only be determined by actually doing the experiment, because otherwise you don't know. As far as you know, in theory, you should get 100%. And then percent yield is calculated as the actual yield divided by the theoretical yield. Let's see. Yeah, let's do one of these real quick and then probably repeat it on Monday, because this is a shorter set of slides. So we're 21 of 37 already. If you've been paying attention, some of the other slide decks have 60 slides. So what are the limiting reactant and theoretical yield if you start with 1.8 moles of titanium and 3.2 moles of chlorine? So the way you do this is just like I did with the pancake example. You basically take each of the reagents that you have quantities for. You calculate how much product each would make, assuming that you have enough of everything else. Then the limiting reactant is the one that gives the smaller yield. And then your theoretical yield is equal to the smaller yield. Okay, so again, still looking at this titanium chloride reaction. So what are the limiting reactant and the theoretical yield if you start with 1.8 moles of titanium and 3.2 moles of chlorine? So like all these other ones, start out with our 1.8 moles of titanium. This is an easier one because we're starting with moles. Doesn't even need to be nearly that long. And then we'll also write out our other stoichiometry problem, 3.2 moles of chlorine. Nope, I want a straight line. There we go. And we'll calculate how much titanium chloride we can make with each of these amounts. So what is our ratio between titanium and titanium chloride? Be brave. That's okay, I never spoke up in class either. Titanium chloride to titanium is going to be 1:1. Right? Both of them have a coefficient of 1. So we can make 1 mole of titanium chloride with 1 mole of titanium. So the yield there, very easy to calculate, 1.8 moles of titanium chloride. Then for our chlorine to titanium chloride, again, the ratio is just the coefficients. So that ratio would be 2 moles of chlorine to 1 mole titanium chloride. Just taking those coefficients. And then we get 3.2 times 1 divided by 2. So there's going to be 1.6 moles of titanium chloride. So which of these then is our limiting reactant? Is it titanium or is it chlorine? Is it titanium? You said titanium? Why do you think it's titanium? Why do you think it's chlorine? Yeah, so the limiting reactant is the one that produces the smallest amount. So it can be deceiving based on the initial amounts because we already have so much more chlorine, but because we need twice as much, that becomes our limiting reactant. That's our limiting reactant. And then what is our theoretical yield? Thought I heard something. 1.6. Yeah, 1.6. So it's the amount of titanium chloride, or the amount of product that's made, with our limiting reactant. Cool. All right, so we'll leave that off there.